Yes, sir. My slide is visible to everyone.
Yes, sir, visible to me, but anyone have issues, then please raise your hand. Right?
Visible to you, it means visible to everyone. There is no issue.
Okay, sir.
Okay, good. Okay, so once again, good evening to everyone. So, welcome to lecture, second lecture, that is the analysis of electrical machines. So, in the last class, we discussed the. Just 1 minute, somebody want to join the class. Yeah, so the last class we started the unit number first. So, that is a basic principle for electric machines analysis. Correct? And in the last class, we discussed about the syllabus, how we can cover the syllabus, how many units, otherwise how many chapters, then cost evaluation scheme, and then little bit discussion on the introduction of electrical machines and electrical drives. So any confusion, any query related to syllabus, related to course evaluation scheme, and just introduction of the electrical machines and drives. Any confusion to anybody? If any confusion, any doubts from the previous class, then please let me know. So we can discuss now and then we can start our next class. I hope there is no confusion because there is I already shared the everything. There is a course curriculum, syllabus, and there is a brief introduction about the electric machines and drive. Correct? Okay. So I hope there is a no confusion from the previous class. So in the today's class, we will discuss about starting with fundamental of electrical machines. Just 1 minute. Yeah, fundamental of electrical machines. Okay. So because 50% of students pass out his degree, BTech degree in maybe the 2012, 2013. So maybe they forget about the fundamental. So I will revise that fundamental concept. So starting with the fundamental of electrical machines, then we can say electrical machines is two types, that is static and rotating. So we can start with the static and rotating electrical machines. In our syllabus for the first semester, that is a rotating electrical machines, correct? So we will start the detail about the rotating electrical machines. So before going to working principle, we have to understand the basic terminology, and that is the most important for the any kind of motor. So there is a AC machine or DC machines. So we will talk about the EMF, MMF, flux, reluctance, and torque of the machine. So these are the fundamental terminology for the electrical machines. Then we will discuss the leakage flux and magnetic fingering. So that is the most important when we will think about the efficiency. Correct? Then operating principle of the DC machines, because starting with the DC machine, because there is a fundamental concept of DC machines. So first we will discuss the operating principle of DC machine, and then in the next class we will start with the induction machines and the synchronous machines. Why first DC machine? Because in the world first we have a DC machine. After that introduced, that is induction machine and synchronous machines. That's why I will start with the DC machine. Okay, and then we can say the Fleming left hand and right hand rule, and that is the most important to find out the current direction, find out the flux direction of the any machines. Okay, so around 6 to 7 topics today we will discuss in the class. Yes, starting with the fundamental of electrical machines, as we know, we cannot create, yeah, we cannot generate and destroy the electrical energy, correct? So, electricity does not exist naturally in any useful form. It has to be generated from any other sources of energy, such as the solar, wind, hydro, thermal, and atom, and etc. Yes, we can say we don't have electricity, correct? Suppose you want to take the direct electricity, otherwise we can say the voltage and current. So we cannot get directly from the nature. It is not available, correct? So we can say fundamental concept, we can say we can not generate any electricity, not generate the energy, just we can convert the energy from one source to another source, correct? So we can say in the environment surrounding us, we have a solar, wind, hydro, thermal, atom, more energy available. So we can convert this energy into the electrical energy, correct? And why electrical energy? Because this subject is electrical machines, correct? So it is required the voltage and current. Photovoltaic cell help us to trap the energy from the sunlight, and generator are used to convert the mechanical power available in the other form to electricity. Yes, the one of the example is a solar panel. We can say the PV, correct? Photovoltaic cell. So all of you know about the PV, correct? So we can say PV is work based on the photovoltaic energy, correct? So we can say many silicon material is there in the solar panel, and then input of the solar panel there is a sunlight, and output of the solar panel there is a DC electric current, correct? So we can say input is a sunlight and output of the solar panel that's a DC. So that DC current we will get from the solar panel, and then we can convert from DC to AC by the inverter, correct? And that is a possible by power electronics converter. The mechanical power can be obtained from the wind flowing the water stream using the turbine. Yes, those who are working in the power plant in the Nepal, they know better about the how we can generate the electric energy, correct? There is a turbine, there is a generator, there is a synchronous generator, correct? And then we can generate the electricity, that is a voltage and current. Motor are used to convert the electricity to mechanical power. So collectively electric machines are devices that convert the mechanical energy to electrical energy, otherwise the vice versa. In the yesterday class, we already seen this thing. Machine we can divide into two category. First is a motor and second one is a generator. So motor is a device that convert electrical energy into mechanical energy. That is a motor. And generator, that is a just inverse of the motor. So we can say we have to give input mechanical power and we will get the output, that is a electrical power. Correct? So we can say machine divide into two categories. That is a motor and generator. Yes. So basically electrical machines are classified into two categories. First one, there is a static electric machine. Yes, static electrical machine is nothing but transformer, and we all know about the transformer, correct? So transformer is a device to transfer the power from one location to another location without changing the frequency. Yes, in the India as well as in the Nepal, supply frequency is a 50 hertz, correct? So supply frequency is a 50 hertz in the India as well as the Nepal, correct? So suppose you want to convert the power from one level to another level, so we can use the transformer. So working principle of transformer is similar to the electrical motor, otherwise the generator. But major difference between the transformer and the rotating machine, that is a transformer is a static device. So there is no rotating part in the case of the transformer. That's why we can say first classification of the electric machines, there is a static electric machine. Yes, we can say machine because there is a convert the energy from one form to another form. Yes, we can say suppose input power supply is a 230 watt. So by using the transformer, you will update the power, you will increase the power level, maybe 230 to 440 watts. So we can say it is a step up transformer, correct? So first one, there is a static electric machine and there is a transformer. Second one, that is a rotating electric machine, and that is a part of our syllabus in the first semester. So rotating electrical machines again classify in the motor. So convert electrical energy into mechanical energy, that is a motor. And second part, that is a generator, convert mechanical energy into electrical energy. So fundamental concept of the electrical machines. Yes, electric machines classify into two category. First one is a static electric machine, and that is a transformer. And why transformer? Because we can say there is a no rotating part in the transformer. That's why there is a best example of the static electric machines. Second one, there is a rotating electrical machines. Then we can say rotating electrical machines, we can say one part is a rotating, that is a rotor. And then we classify there is a motor and the generator. Okay, so this is the fundamental concept of the electric machines. Those who completed the BTech in the before the 5 to 6 year and maybe they forgot about this fundamental concept. So that's why I cover this thing in the class. Yes. Now little bit about the static electric machines. So I'm not spending the too much time on this topic. There is a transformer. Just overview of the transformer. Okay. So static electrical machine, yes, there is a transformer, and this is the structure of the transformer. So you can see this is the design by ABB, and there is a reputed company to design the transformer. Correct. So static device then that can transfer the alternating current. Yes, transformer is always working on the AC. Correct. Alternating current from one circuit to the another circuit by electromagnetic induction. Yes, this term is most important, electromagnetic induction. Why? Because most of the in motor that is working on the electromagnetic induction principle, correct? And same transformer is also working on the electromagnetic induction. Can be considered as a transformer. Okay. Transformer are used to transform the alternating current from one voltage level to the another voltage level. So we can say step up transformer, and we can say step down transformer. And third one is a we can say the auto transformer. Third one is a auto transformer. Correct. So all of you know about this transformer, correct? Because most of the student you are working in the industry, and that is a core electrical industry. So I hope you should know about the transformer. Okay, and maybe you are a core team member for this transformer testing, correct? So a basic transformer consists of the two coil that will couple using the magnetic core. Yes, so basically for the transformer we can say the primary coil and secondary coil. So you can see this is transformer diagram. So we can say this is the primary coil, there is a primary circuit, and this is the secondary coil. So we can connect our load. So we can say this is the load, correct? So lamp load. So input power supply, there is a sinusoidal supply, maybe the 230 volt, maybe the 440 volt, depend on the transformer type, correct? And maybe you will get the output from the secondary winding, maybe the 440 volt, maybe the 230 volt, maybe the step up, yeah, step down, correct? So you can see the both winding, there is a primary winding and secondary winding, it is isolated. There are no physical connection, but it is a magnetic connection. So we can say couple, correct? So both are coupled through the magnetic core. So this is the magnetic core. So this is the magnetic core, correct? So we can say, yes, in the case of the transformer, both winding, there is a primary and secondary, both are not physically connected, but it is a virtual connection by the magnetic core. Okay, so this is the magnetic core and this is a flux is flowing. Okay, in the case of the three-phase transformer, two set of the coil per phase will be present. Yes, we can say single phase and three-phase transformer. I will not discuss about the three-phase as well as single-phase transformer. My main target is just overview of the transformer. Correct. One set of the coil is known as the primary winding, and another coil is a secondary winding. Yes, from the primary winding we can give the input power supply, and from the secondary winding we will get the output. Correct. These two windings are insulated from each other. Yes, both are the insulated to each other, are magnetically coupled through the iron core. Yes, as I said, so there is a magnetically coupled circuit. Okay, and both are the not physically connection, but both are connected to the magnetic core. Correct. So this is the just overview of the static electric machines. Yes, the alternating voltage is connected to the primary supply winding. I already discussed this thing in the previous slide. So this equation, it is a most important equation whenever we discuss the transformer. So we can say transformer ratio. Okay, transformer ratio. So V1 upon V2 is equal to N1 upon N2 is equal to E1 upon E2 is equal to I2 upon I1. So you can see voltage, number of turns, back EMF, all are equal, but current relation, there is a inversely current relation. Correct. So what is a V1 and V2? So V1 and V2 are the voltage in the primary and secondary side of the transformer respectively. So V1 stand on the primary voltage and V2 stand on the secondary voltage. Similarly, N1 and L2, N1 there is a number of turns of the primary side and N2 there is a number of turns in the secondary side. Correct? E1, E2, there is an electromotive force. Yes, because of the magnetic core, so it will generate the electromotive force. Correct? And what is the electromotive force? We will discuss in the next slide. So E1 and E2, E1 for the primary voltage and E2 there is a secondary voltage. And I2 and I1. So I2 there is a secondary voltage and I1 that is your primary voltage. Okay. So this is your I1 that is your primary and I2 that is the secondary side of the transformer current. Correct. So yes, student, please remember this equation. I hope all of you know about this relation. Okay, if you forgot this relation, then please revise this relation. That is the most important for your job as well as the for this course syllabus. Okay. Yes, step up and step down transformer. We can say if the secondary voltage is greater than the primary voltage, then we can say it is a step up transformer. So step up means suppose your supply voltage is 230 and you will get output maybe the 440 volt. Then we can say step up. Primary voltage is greater than the secondary voltage, then we can say step down. Suppose your supply voltage is 230 volt and your output is maybe the 130 volt. So you will get the lower voltage, correct? Then we can say it is a step down transformer. So mostly we can use the step up, otherwise the step down transformer. And auto transformers mostly we can use in the testing of the transformer, otherwise in the case of the laboratory work, correct? So we can regulate the voltage. That's why we can use the auto transformer. Yes. So this is the brief about the static electric machine. So we can say there is no rotating part in that device. Okay, so we can say device name is a transformer. And yes, transformer is working on the electromagnetic induction principle. So primary winding as well as the secondary winding both are isolated to each other, but magnetically coupled to the each other. Okay. Working principle is everything same. Only difference is there is a static device. There are no rotating part. Second type of electric machines, there is a rotating electrical machines. And whenever we can say the rotating electrical machines, then we can say we have a two component. One is the motor and other one is a generator. Let's see what is a rotating electric machines. So definition of the rotating electric machines. Electric machine is the general term in the electrical engineering for machine that use the electromagnetic force. Yes, transformer, we already seen in the transformer there is electromagnetic force EMF, correct? So electromagnetic force is nothing but EMF. This machine include the electric motor and electric generator, correct? The rotating electric machine use either convert the mechanical energy to the electrical energy or vice versa. Yes, we can say, suppose you have a motor, then we can say convert the electrical energy into mechanical energy. But if you have generator, then we can say convert the electrical energy into, mechanical energy into electrical energy. There are the three basic type of the rotating electrical machines. Yes, we can divide rotating electrical machines in three category. First one, that is a DC electric machines. So we can say DC motor, otherwise the DC generator. Correct. Second one, there is a synchronous machine. We can say alternator, otherwise the synchronous motor. Correct. Otherwise we can say synchronous generator, otherwise the synchronous motor. Third category, that is an induction motor or a synchronous machine. So we can say we can classify the rotating electrical machines in further two category. There is a electric motor, otherwise the electrical generator. Again, we categorize this motor and generator in three category. There is a DC electric machines, synchronous machines, otherwise the induction machines. Correct? All rotating electric machines have the two basic part in the common. First one, there is a rotating part known as a rotor. Yes, so this is the first part and this is the second part. So first one, there is a rotor and rotor is a rotating. And second is a stationary part and called the stator. So we can say this is the first part. So we can say first is a rotor and second one is a stator. So rotor, there is a rotating part. So maybe in the case of the generator as well as the in the case of the motor, correct? In the both case, we have a rotor. Without rotor, we cannot design any type of the rotating machines. Okay. And second part, there is a stator. There is a steady, otherwise stable part. Otherwise, we can say the stable part. So stator is not rotating, but rotor is always rotated. Correct. So these are the two major components in the case of the rotating electric machines. First one is a rotor, and second one is a stator. Yes. Now type of the magnets. Why we have to discuss the type of magnets? Because before going to detail analysis of the machines, because subject name is a analysis of the electrical machines, so we have to analysis the each and every component of the rotating machines. So whenever we can say analysis means we have to analysis the voltage, current. So we have to analysis the analysis of first one, there is a voltage, second one current, third one speed, fourth torque, fifth flux, sixth reluctance, seven inductance, and eight impedance. Correct. So we have to analysis total 8 parameters of the any kind of motors, yeah, any kind of generators. Then we can say we are doing the analysis of the electric machines. So type of magnets. So whenever we can say flux, so that flux is component under the category of the magnets. So that's why I starting with the fundamental concept of the magnets. So we can say across the world we have a two type of magnets. So there is a natural magnets, otherwise the permanent magnets. So we cannot design, we cannot create this magnet, and that is a naturally available material, that is your permanent magnet. Otherwise, we can say the natural magnet. Second category, that is electromagnet, otherwise the artificial magnet. Yes, this magnet we can design. That's why we can say there is an electromagnet, otherwise the artificial magnets. But this category we cannot design. This is the by the we can say that is a gift from the nature. Correct. So we can say yes, in the China, USA, in that country we can find the magnet resources. That is a natural magnet resources. Suppose you want to design the electromagnet, yes, we can design the electromagnet by the winding on the iron bar, and then we have to just supply the electric current. We can use the both type of magnet to design the electrical machines. Why we are discussing this magnet? Because we have to design the motor, correct? We have to design the machines. So maybe you can use the natural magnet, otherwise maybe you can use the artificial magnet, correct? Magnet are compulsory component in the case of the electrical machines. Yes, maybe somebody say I can make the machines by the stone. That is not possible. Magnet is a compulsory, correct? To design the any kind of electrical machines. So electrical machines means there is a rotating electrical machines. That is a compulsory. Without magnet we cannot make the electrical machines. So that's why I cover this topic. There is a type of the magnet, correct? So we can say the natural magnets, and there is a artificial magnets, otherwise the electromagnets. How we can make the electromagnets? Yes, so this is a fundamental concept already we studied in the standard 11th 12th as well as BTech. Still I cover this topic because maybe you forget about the electromagnets, so that's why I want to cover this thing. So you can say this is the inside, so we can say this is the iron bar. Okay, so this is the iron bar, and this is your winding. We can say this is your winding, correct? And we can give the power supply, correct? So this is your current, so you can supply this current, so current is flowing from this direction and flux will generate. So you can see the current direction is this side, so we can say the inside, correct? So we can say flux is produced in the clockwise direction, correct? In the second diagram you can see just the reverse. So suppose you want to make the motor in the clockwise direction rotation, correct? Suppose you want to rotate your motor in the clockwise direction, then you can give current in the clockwise direction. Suppose you want to rotate your motor in the anti-clockwise direction, then you have to just change your connection. In the previously maybe the positive to negative, now you can just convert, change the connection, that is a negative to positive, correct? And then we can create the your electromagnet. Yeah, so this is the just fundamental concept of the electromagnet. So how we can make the electromagnet? It is a required only one iron bar. So we can say this is your iron bar. Yes, so this is your iron bar, and one more component is required. That is a winding, correct? So we can say this is the winding, and just give the power supply, there is a current, and then it will create the flux, correct? And we can say it is a your electromagnets. Okay, so yes, what we can do with the force, correct? How we can generate the force? So you can see this is the electromagnetic force. Yes, we can say this is electromagnetic, and figure B, there is your permanent magnet that is available by naturally, correct? We can say it's a natural resources. So we can say north pole and south pole, but in the case of the electromagnet we have to create the north pole and south pole, correct? And yes, flux line is passing from the north to south, that is the for the electromagnet as well as for the permanent magnet. So flux line is always passing from the north to south in the both case. So this line belong to the many properties. So you can see this is the your flux line. Okay, so this is your flux line. Flux line, we can say the flux line, correct? And this flux line, there is a most important for the electric machines. Without this flux line, force will not generate, and suppose force will not generate, then motor is not able to produce the torque. So this line belong to the many properties. First one, never interact with each other. Yes, there is a never interact with each other. all are identical and equal in the intensity. Yes, we can say suppose one flux line there is a 1 Weber. So we can say all the line there is a 1 Weber, correct? So there is a not like that first is a 1 Weber, second one is a zero point 0.5 Weber. It is not like that. Take the shortest path with the least resistance between the pole. Yes, in the case of the same electric current, we can say electric current is flow with the minimum resistance path, correct? So same in the electromagnets, flux is path in the shortest with the least resistance. The intensity of the line decrease as distance between the poles increase. Yes, suppose distance is increased between the two poles, there is a north pole and south pole, correct? Then the intensity of line is decreased, correct? The heading from the south pole to the north pole inside the magnet and vice versa outside. The static line do not move and impose the trend as if they are moving. So these are the some properties of the magnetic force, a magnetic flux line, correct? If student, if you have any confusion, then please let me know because this is a fundamental concept. Okay, so still, if you have any confusion about the fundamental concept, then please let me know. Yes, how we can find out the magnetic field lines, correct? So there is a, maybe you heard about the Fleming left hand rule and right hand rule, correct? So by using this rule, we can find out the current direction. So magnetic field is induced when an electric current passes through the conductor. Yes. How magnetic field is induced? Suppose we have a iron bar and we can wind on the iron bar. There is a, any copper wire and then pass the current. Correct. So there is a field is induced, and generated magnetic field lines will be directed to the direction of the current passing to the conductor. Yes, in the previous slide we see, suppose this is the coil, correct, and we can pass the current. So this flux line will produce, correct, and this flux line is always north to south, correct. But how we can find out the direction of the current, correct? So this phenomena can be observed by taking the isolated state conductor passing through the center of the carton plate is seen in the figure 1. Yes, suppose this is the conductor, we can pass the current. So this is the magnetic field line, correct? This is the direction of the magnetic field line. But how we can find out the direction of the field line? So by the Fleming left hand rule, correct? Sorry, by the Fleming the right hand rule, correct? The direction of the generated field lines in the conductor, by Fleming the right hand rule, we can find out the direction of the magnetic field as well as the direction of the current. So we can say yes, we have a Fleming, we have a right hand rule. Then thumb indicate there is a direction of the current. So you can hold the wire, correct, and then we can say your thumb, that is a indicate your current, and your figure, that is a indicate your direction of the magnetic field. So there is a fundamental of the Fleming right hand rule as well as the Fleming left hand rule, correct. So right hand rule we can use in the case of the motor, and left hand rule we can use in the case of the your generator, correct. Yeah, so magnetic field describe the most of the major function is the line force that give the number and the total called the magnetic flux. Okay, so this is the magnetic flux, and magnetic flux is nothing but phi, and we can indicate there is a symbol of this flux, that is a phi. Just, yeah, and unit is a Weber. Yes, students, unit is the most important. Is we are engineers, then we have to define the proper each and every component. So magnetic flux is represented by the phi, and unit is a Weber. The flux flow of the magnetic flux represented by the line of the force that move between the pole of the north and south pole of the magnet. Correct. So you can see this is the maybe the conductor 1 and conductor 2. both are the current carrying. So we can say it by the right hand rule, by the Fleming right hand rule, we can find out the current as well as the flux direction. The property of the magnetic field are given by the density of the line at a certain point in the field, and this is the called the flux density. Yes, we can say whenever current carry conductor put in the magnetic field, it will create the flux, correct? But what is the density? What is the density of the flux? So that thing, it is a, we can say how many lines are there. Then we can say it is a flux density, correct? The property of the magnetic field are given in the density of the lines at a certain point in the field. Then we can say it is a flux density. And symbol of the flux density, that is a B. We can represent by the B, letter B. And that is a capital letter B. And unit is a Weber per meter square. That is a Weber per meter square or Tesla. Okay. So we can say first component, there is a magnetic flux, and that represent by the phi, and unit is a Weber. Second one, we have to find out the density. Okay. Then we can say Weber per meter square. Whenever we can say density, then we can say we have to cover the area. And unit of the area, that is a meter square. So we can say flux density, that is a unit of the flux density, that is a Weber per meter square. Yes, so we can say formula, the 1 Weber is equal to 100 million field lines. So we can say 1, 2, 3, 4, 5, 6, 7, 8. So up to 100 million field lines. Then we can say it is a Weber. So 10 to the power 8. So this is the not 108. So this is a 10 to the power 8. 10 to power 8, then we can say it is your 1 Weber. Okay. So 1 Weber means 100 million field lines. Then we can say it is a 1 Weber. And that formula is a B equal to phi into phi upon A. It is a flux. Okay. So we can say B is equal to phi upon A. So B, that is your plus density, correct? And phi, that is your flux, and A, that is the area. So where A is the cross section area, unit is a meter square, where the density of the lines to be the found. Yes, so phi, we can say the flux. B, that is your flux density. So we can say B is equal to phi upon A. So based on that formula, that is a B equal to phi upon A, we can cover the one numerical. So example, what is the density of the flux in the area of the number of lines passing to the rectangular of the 40 into 25 to 50 centimeter, which is the 12 million lines. So your target is you have to find out the flux density. So what is the answer? So based on this formula, we have to find out the flux density B. We have to find out the B. Correct? So how we can find out the B? Yes, student. Any guess? What is the answer? So you have every data. Yes, you have to convert the unit, because this is the centimeter and standard unit is a meter. Meter. And you have also flux line. Correct? So 12 million lines. So we have to apply the formula, that is a B equal to phi upon A. We have a flux value, we have a area value also. Area value is a 40 into 250 centimeter. So we have to convert into standards units, so that is into meter, correct? So answer is, we can convert the number of lines to the Weber, where the Weber equal to the 100 million lines. So we can say phi 12 into 10 raised to power 6, because this is a 12 million lines, divided by 12 into 10 raised to power 8. So we can say flux value is a 0.12 Weber. Yes, flux value is a 0.12. So we can say flux equal to 0.12 Weber. Now what about the area? So area, that is your 40 into 250 centimeter. So we have to convert into a meter, correct? So we can say 40 into 250 into 10 raised to minus 4. So we can say 1 meter square. So finally answer B equal to phi upon A. So phi value we got, that is a 0.12, and area, that is your 1 meter square. So we can say phi is a your flux density is a 0.12 Weber per meter square. Correct? So this is a simple example. So, but please remember there is a formula of the flux density, that is a B equal to flux line divided by your area. Okay, so that is the most important. Okay, now magnetomotive force, MMF, correct? So MMF, the number of lines of the magnetic force, otherwise flux, that is a phi, generated by the solenoid is directly proportional to the current, that is a passing of the current, and number of turns, correct? So how much MMF will generate? So that is a depend on the current value and number of turns. Suppose I can say this is your solenoid, correct? So we can say this is a solenoid wire. So this is a solenoid, we can say solenoid. And this is the number of turns. And I am passing the current from here to here. So what is the amplitude of this current and number of turns? How many number of turns? Then we can say there is a MMF. MMF is number of turns into current magnitude. So that is a MMF. So we can say MMF, there is a product of the number of turns into current. Correct? So that is a MMF. And it is represented by the capital F, and unit is a ampere into ton. Ampere, there is a unit of the current, and number of tons, that is a T. Okay, so unit is a ampere into tons. Okay, yeah. So second formula, that is the most important, that is a ampere into tons. Sorry, MMF formula. First formula, that is a flux density B equal to phi upon area. And second formula, that is the most important for the machines, MMF, that is a N into I. Third one, there is a force. The amount of the force generated, yes, amount of the force generated depend on the current of the current, yes, of the current is on the current of the current, the intensity of the force line of the field, there is a B, and the effective length of the conductor within the field, there is a length of the conductor, how much long conductor, which is usually equal to the length of the electrodes. So we can say force, how much force will generate, that is a your flux density into current and into length of the conductor. Okay, so that is your force, BIL, and depend on this force we can say torque will generate, correct? So we can say, suppose force is maybe the 5, correct? Then we can say depend on the force, that is a generate torque, your torque. So third formula, there is a force, how much force will generate, there is a BIL. Okay, so B, unit of the B, the Weber, current, there is a ampere, and length, there is a meter square. Okay, the value of force increase when the value of the any amount of the right hand side equation is increased. Yes, we can say the F directly proportional to the B, I, and L. So we can say any one quantity will increase, then ultimately increase the your force. Okay. Yes, in the case of the rotating part, so we can say rotor is rotating. So what about the force? When the direction of the conductor movement within the magnetic field at a certain angle, yes, we can say this is the your rotor, and your rotor is rotating continue. Correct? Maybe somewhere here, maybe somewhere here, maybe somewhere here, maybe somewhere here. Then how we can find out the force? Correct? Then we can say same formula, but now we have to add the sine theta, correct? So we can say force is equal to BIL sine theta. In the case of the charges and voltage, so we can say force equal to B. Q indicate there is a charge and V indicate there is your voltage. Okay, so we can say yes, this is a I. We can replace I by Q into V, correct? So there is a B into Q into V into sine theta in the form of the your charges and in the form of the voltage, correct? Yes, now we can take one example based on the force. So when 20 centimeter conductor is passed in which current of 20 ampere, yes, current is a 20 ampere, within the magnetic field, the force exerted on the conductor is 24 Newton. What is the density of the lines of the field flux? Line of this field, correct? So length of the conductor is given, there is a 20 centimeter. Current is given, there is a 20 ampere. Force is given, there is a 24 Newton. Then we have to find out the density. Yes, just apply the formula. B equal to, so formula is a B equal to sorry, force equal to B into I into L. Correct? So this is a formula. So we have to find out this is a B. We have to find out the B. So we can say B equal to nothing but force upon I into L. Correct? So this is the same formula. Correct? Force. We have a force that is a 2.5. Okay. There is a 24, not 2.5, 24. Correct? 20 into 20, that is your, we have to find, convert into area square, that is the meter square, correct? And 20 ampere your current. So you will get this answer. Okay. So there's a 24 Newton meter. So this is a 24. Okay, not 2.5, 24. 20, there is a length. We have to convert into meter square, correct? So that's a 10 raised to power minus 2. And current, there is a ampere, there is a 20, correct? So you will get 0.6 Weber per meter square. There is an answer. Okay. Yes. So till now, there is a fundamental concept about the electromagnets, permanent magnets, field flux, field density, and that is the most important for the understanding of the electric machines. Now we can say analogies between the electric machines and the electric circuit. So analogies means we can say we have a simple circuit. We can say we have a closed loop. So this is a circuit, correct? So current is flowing I. Current is flowing I, correct? So we can say current is flowing. Suppose VDC is a 20 volt, correct? So depend on the 20 volt supply voltage, depend on the resistor value and depend on the inductor value, current is flowing, correct? So we can write the equation V equal to R Ri plus L di by dt. So we can write the KVL equation, correct? So this is nothing but KVL equation. KVL, that is a Kirchhoff voltage law, and KCL, that is a Kirchhoff current law. So we can write the KVL equation for this circuit. So V, that is a supply voltage, is equal to R into I, yes, current flowing through the resistor, that is I, plus L di by dt, current flowing through the inductor, that is L di by dt. Then what about in the machines? What about in the machines? So we can say this is your machines, correct? So we can say yes, we can say this is a north and this is a south. And we can say this is your supply winding, correct? And you can say just it is your supply voltage, correct? Maybe we can say the DC supply VDC, and your flux is passing to this stator. So we can say this is your flux. So we can say this is your stator and this is your rotor, correct? So now what is the relation between the electrical circuit? So we can say this is the electrical circuit and this is your magnetic circuit. So you can see in the both circuit, we have to give the VDC, yeah, maybe the VAC, depend on the type of the motor, correct? And once you supply the voltage, then obvious current will flow, correct? And once the current will flow, then it will create the flux. And flux is continue circulate in the stator, and depend on the electromagnetic induction effect, it will pass in the rotor, correct? And rotor is able to rotate in the clockwise direction, maybe the anti-clockwise direction, correct? So we have to analysis the what is the analogies between the electrical and magnetic circuit. So you can see by the loop wise both are similar. We have to give the power supply, there is a voltage, then current will flow because circuit is completed, that is a closed loop. Okay, then current will flow, and whenever current carrying conductor put in the magnetic field, where magnetic field, because this is the magnet, because of this magnet it is a magnetic field. When current carry conductor put in the magnetic field, it will create the force, correct? So we have to analysis the analogies between the electrical circuit and the magnetic circuit, correct? So analogies between the electrical and magnetic circuit, first one is a driving force. Apply battery voltage, there is a E or V. Apply ampere turns, that is a AT or the NI, correct? Response, we can say response current, there is a division of the force divided by the electric current, electric resistance. So we can say I equal to V upon R, otherwise E upon R. But in the case of the magnetic circuit, there is a force, flux, we can say flux, not the force, but flux, we can say driving force divided by the magnetic resistance. So we can say AT upon R, and R is nothing but your reluctance, okay? And we can define L upon A. So R is nothing but L upon A into mu, and that is your reluctance, AT upon Weber, okay? So that is your flux R, L upon A into mu, and mu is nothing but mu naught into mu R. So we can say mu, and mu naught, that is your air permeability, and mu R, that is your relative permeability, okay? And A, that is the area of the magnetic path. What about impedance? So we can say in the case of the electric circuit, R equal to rho into L upon A. Here L, there is a 2 pi R. Yes, we can say simple length of the conductor. But in the case of the magnetic circuit, there is a reluctance L upon mu naught into mu R into A. Correct? So we can say R is nothing but, reluctance is nothing but R is equal to L upon mu into A. Correct? Equivalent circuit, you can see this is the equivalent circuit for the electrical circuit, and this is the equivalent circuit for the magnetic circuit, which you can say force, that is a Ni, flux, yes, instead of the current, here flux is there, and in the electrical circuit there is a resistor, and here is a reluctance. We can also represent the reluctance by the letter S. S is nothing but your reluctance. In the sum book, it is written by the letter R. In the sum book, it is written by the letter S. Correct? But in the electrical circuit, it is always R for the resistor. So it is a good, we can represent the reluctance by the letter S. Okay, so this is the equivalent circuit for the your magnetic circuit. Yes, field intensity. So we already studied that is a field density, but what about the intensity? So field intensity, so magnetic field intensity, when the magnetic, just when the, just a minute. Yes, when magnetic field intensity, it is represented by the H. When magnetomotive force (mmf) is applied to the homogeneous iron rod, there is a produced within the material in the magnetic potential gradients is given by H. So H is nothing but Ni upon L. And unit is a ampere turn divided by M. That is your H. Okay, so it is a magnetic field intensity H equal to Ni upon L. Otherwise, we can say close integration of H into dl is equal to Ni. Okay, but in the case of the electric, in the case of the electrical, you can see epsilon equal to E upon L. Correct. Otherwise, the close integration of the epsilon into dl is equal to E. So this is the similarity between the electrical circuit as well as the magnetic circuit. Yes, voltage drop. So we can say in the case of the voltage, we can say V equal to IR, and in the case of the magnetic circuit, we can say Ni. There is a flux. Current density, we can say ampere upon meter square, but in the flux density, we can say the Weber upon meter square. Otherwise, we can say phi upon A. So this is a different. I am not going to explain this different. You can just go through upon the difference between this difference is based on this table. Yes. Now we move ahead with the analysis of the magnetic circuit. Okay. Now we can start the analysis of the magnetic circuit. Yes. We already studied this term. There is a electric field term, magnetic field term, electromotive force, EMF, and magnetomotive force. This term we already studied in the previous slide, correct? So we have to analysis this component whenever we can say analysis of the electrical machines. Yes. So magnetic flux, there is a B equal to phi upon A. We already discussed. So this is the detailed analysis. We can say the detailed explanation of the magnetic flux as well as the flux density. Okay. So there is a no new in this slide. Okay. That's why I'm skipping this slide. But you can go through this slide because this is a detailed explanation. So suppose magnetomotive force we already discussed in the previous slide, but here I written the in the detail a measure to ability of the coil to produce the flux line is called the magnetomotive force. So definition of the magnetomotive force is a measure of the ability of the coil to produce the flux. How much flux is produced? How much? How we can measure? There is a magnetomotive force, correct? And magnetomotive force is nothing but N into I. Flux density. Sorry. Yes, flux density. Otherwise, the flux strength. Otherwise, the density we can say H. Otherwise, the flux intensity. Correct. So H is equal to Ni upon L, and this is the unit ampere turn upon meter. Correct. And flux density there is a B is equal to mu into H. Okay. And we can say mu is equal to mu naught into mu R, where mu naught is equal to absolute permeability of the free space and is equal to 4 pi into 10 raised to power minus 7 H upon M. H, that is a Henry per meter. Correct. And mu R, that is a relative permeability of the medium. So we can say flux density B equal to mu into H, otherwise B equal to pi into A. Sorry, pi upon A. Okay, so we can say B equal to phi upon A, otherwise B equal to mu into H. And H is a intensity of the magnetic field, correct? Otherwise the strength, okay, intensity, otherwise the strength. Yes, as I said in the previous slide, so reluctance, it is a similar to the resistance, but it is a symbol is S, because most of the time we can represent the reluctance, there is a letter S, and in the case of the electrical circuit we can represent by the R, that is your resistance. But in the both case there is the same work. Reluctance, it is the opposite of flow of the flux. In the case of the resistor, this is the opposite of flow of the current. So we can say reluctance, that is directly proportional to the L upon A. So there is a length upon area. Okay, so reluctance, that is a length upon area, and unit is a ampere turn per Weber. Yes, otherwise we can say reluctance, that is a mmf upon flux. Second formula, that is a mmf upon flux, so that is a reluctance. Yes. Please go through this slide. So there is a just it is explained, there is a reluctance, how we can represent the reluctance, and when comparison between the magnetic circuit laws, so there is a current versus the reluctance, because current versus flux, current, there is a electrical circuit, and flux, there is your magnetic circuit. Okay. Yes, magnetic circuit law. So we can say, suppose we have a resistor, there is a series connection resistor. So we can say resistor, there is a R1 plus R2 plus R3. Correct? Suppose that resistor is connected in series. But in the case of magnetic circuit, so how we can represent the reluctance? So reluctance also same, S1 plus S2 plus S3 up to Sn. It is the same. Done? So this is a similarity between the electrical circuit as well as the magnetic circuit. Yes, what about the resistor? Suppose is connected in the parallel in any one student. Suppose resistor is connected in parallel, then what is the equivalent resistor? Suppose R1 and R2. Then how we can write the equivalent resistor? Yes, any one student?
R1 multiplied R2 divided R1 plus R2.
Yeah, good. So 1 by R1 plus 1 by R2 up to 1 by Rn. Correct? So we can write in the series connection there is R1 plus R2 plus R3, but in the case of parallel there is a 1 by R1 plus 1 by R2 up to 1 by Rn. Okay. So similar we can write for the reluctance. So there is a S1 plus S2 plus S3 up to Sn. Similarly for the parallel connection, so we can set the parallel connection 1 by S1 plus 1 by S2. Correct? So it is the same. We can set the magnetic circuit as well as the electric circuit. Yeah, you can see here. There is a parallel circuit. Correct? Yes. So till now, any confusion, any query? Yes, student. Any confusion, any query till now? Okay. Done. So now is a leakage flux. So leakage flux, we have to discuss the leakage flux because we have to ultimately analysis the electrical machines, and we have to find out the efficiency. So leakage flux, a part of the magnetic flux that does not flow in the desired path in the magnetic circuit is known as the leakage flux. Suppose that flux line is from left to right side, correct, and it is a pass to the secondary side, correct. But some part, maybe it is a node, some line it is a node pass in the secondary side. Then we can say it is a leakage flux. So you can see this line, there is a leakage flux, correct, and this line it is called the fingering effect. So some flux line, there is a flow in the air, correct? Then we can say it is a fingering effect. Yes, so what is a leakage flux? The most of the practice magnetic circuit, the path of the large part of the magnetic flux is through the iron part of the magnetic circuit, and rest of the part in the magnetic flux flow through the air. So whatever flux line is passing to the air, then we can say it is a leakage flux. Magnetic flux in the air known as a useful flux, that is a 5G, since it can be used for the various useful purposes. So whatever flux line passing to the air and it is a club in the secondary side, then we can say it is a useful flux. But suppose flux line passing to the air gap, but it is a not going to the secondary coil, then we can say it is a losses, otherwise the leakage flux. Okay. So here I written the total magnetic flux produced by the coil does not pass to the air gap, that is a some part of the leak through the air surrounding of the iron core. This magnetic is a core as the leakage flux. So you can see the figure 1. So this figure 1, correct? Then so we can say it is a leakage flux. So yes, formula we can say total magnetic flux produced by the machine. So that is a phi I, correct? This is a air gap flux. So we can say the leakage flux equal to phi I minus phi G. So phi G, that is your phi I, that is your total magnetic flux, and phi G, that is your air gap flux, correct? So we can say leakage coefficient flux in the iron core divided by flux in the air gap core. So that is a simple. So we can say leakage flux is nothing but whatever flux line passing to the air gap, but it is a not going to the another coil, then we can say it is a leakage flux. And magnetic fingering, yes, so this effect is a magnetic fingering. When the magnetic flux line pass to the air gap, they tend to blur out. So this is a figure 2. Yes, you can see this line. It is because of the magnetic field line repel to each other when passing to the air. This is known as the magnetic fingering effect. So this is again there is a losses. So we can say leakage flux is also losses, and magnetic fingering also losses. Okay, so we have to avoid these two things, that is a leakage flux as well as the magnetic fingering effect. So suppose magnetic fingering effects is there, then what is happening? So due to the magnetic fingering, the effective area of the air gap is increased. Yes, effective area of air gap is increased, so ultimately reduce the efficiency, and thus magnetic flux density is decreased in the air gap. Yes, effective area is increased, then we can say flux density is decreased. Longer the air gap, the higher the fingering, and vice versa. Yes, longer the air gap, then fingering effect is high, otherwise the vice versa. Fingering effect increase with the increase the air gap length. Fingering is directly proportional to the air gap length. Yes, so we can say the suppose air gap is high, then fingering effect is high. Yes. Now we are going the core analysis of the electric machine. So there is a rotating machines, correct? But still there is a fundamental concept. From the next class we will move in the analysis part. There is a totally mathematical component, correct? So now I have a last component here. There is a rotating machines, correct? So just repeating this part, there is a rotating machine is nothing but AC machine and DC machine, and we can say electrical energy into mechanical energy and mechanical into electrical energy, correct? Yes, DC machines. So we can say we have a two type of machines, that is AC machines and DC machines. Yes, DC machine we can classify again into three categories: series machine, shunt machine, and compound machine, otherwise separately as certain machine, correct? So DC machine convert electrical energy to mechanical energy, yes, but supply voltage is DC. That's why we are saying it is a DC machine. Suppose you are giving the supply AC, then we can say is a AC machine, like an induction machine, synchronous machine. But in the case of synchronous machine, there is a double feed machine, we can say, because in the stator winding we have to give the AC supply. In the case of the rotor winding, we have to supply the DC supply. That's why we can say it is a double feed machine. But suppose induction machine, then we have to just supply the AC supply, and for the DC machine, just we have to supply the DC voltage. Okay. Working principle is as I said in the beginning of the class, DC machine is the first introduced in the market. So that's why we have to start with the DC machine. Then we will discuss the induction machine, and after that we will discuss the synchronous machine. So what is the working principle of the DC machines? The working principle and the operation of the DC machines are based on the effect when the current carrying conductor coil lying in the magnetic field, the magnetic field produce a mechanical force. It known as a torque which rotates the conductor coil in the magnetic field. So, simple definition: whenever current carrying conductor put in the magnetic field, okay, and how we can generate the magnetic field? By the electromagnet, correct? So we can say whenever current carrying conductor put in the magnetic field, it will produce the magnetic force, and this magnetic force is nothing but your torque. And once the motor produces the torque, then it is able to rotate your motor. So sequence is, you can see voltage, then we can say flux, then we can say MMF, then we can say EMF, then we can say the torque, and then we can say the speed. So this is the sequence. So you have to supply the voltage. Obvious, by voltage there is a current, correct? Then flux, then MMF, then EMF, and then torque, and finally speed. Then motor is able to rotate. Maybe the end speed, yeah, maybe the omega speed, correct? The direction of this produced the torque can be found by the Fleming left-hand rule. That is a thumb, correct? So we already seen the Fleming left-hand rule, correct? That's why I covered the first Fleming left-hand rule, correct? So by the direction of we can find out the direction of the current by the Fleming left-hand rule. That is a force as well as the direction of the current. So how much force is generated? We already discussed, that is F equal to BIL. Just 1 minute, somebody want to join the class. Yes. So we already discussed that is the force, that is the BIL. B, that is your flux density, unit is a Tesla. I is nothing but your current, and L is nothing but your length of the conductor, and unit is a meter. So this is the Fleming left-hand rule and right-hand rule. Fleming left-hand rule and the Fleming right-hand rule are essential rule to applicable to magnetism and electromagnetism. Yes, because we have to find out the current direction, we have to find out the force direction. So it is introduced in 19th century. Okay. Yes, this line is most important. It is important to note that these rules do not determine the magnitude. It is a not determine the magnitude. It is only determine the direction. Okay, so we can say this is the only scalar quantity, not the vector quantity. So Fleming left-hand rule and right-hand rule both are the scalar quantity, not the vector quantity. In the scalar quantity, we can know only the direction, not the magnitude. But in the vector quantity, we can find the both magnitude as well as the direction. Correct? So instead, so only the direction, the three parameters, that is the magnetic field, current, and force. When the direction of the other two parameter is the, yes, so we can say by the Fleming left-hand rule and right-hand rule, we can find out the direction, not the magnitude, and direction of the magnetic field, current, and force. Yes. So you can see the Fleming right-hand rule. So thumb, that is indicate the thrust, otherwise motion. First finger, that is your magnetic field, and ring figure, that is your current. Okay, so this is your Fleming right hand rule. Fleming left hand rule, again thumb, that is your motion, magnetic field, and this is your current. Okay. Yes. Okay. Yes. So DC machine, basic principle of the DC machines. So we can say this is your battery. So we can say this is your battery. Okay, maybe the 10 volt. Okay, so we can say current is flowing from. So we can say this is positive, this is a negative. Current is flowing this direction, anti-clockwise direction, from here to here to here to here. Correct. So we can say current is flowing from here, 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 here. And this is the north pole and this is the south pole. So we can say that we have a permanent magnet. So this is the north pole and this is south pole. So we can say whenever current carrying conductor put in the magnetic field, yes, so this is a current carrying conductor we put in the magnetic field, it will create the force. Correct. So you can see this is the magnetic field. So flux line is produced from north to south. Yes, north to south, and it is able to rotate this motor. Correct. So you can see this is a rotation. Correct. And this is the commutator. Why commutator? Because your conductor is rotating. Correct. And your connection is fixed, so that is not able to rotate the part. Correct. So that is a commutator. So commutator work is a reverse the current. So we can say commutator is nothing but mechanical inverter. Correct. Mechanical converter. So work of the mechanical commutator is nothing but reverse the direction of the current. And then is a brushes is there. So what is the use of brushes? So use of brushes to collect the current. Correct. So just see the any video from the YouTube. So working principle of the DC machine. I am not going to explain the step by step process because this is a BTech level. You already studied this thing in the BTech level, correct? So just I introduced this concept because for your revised concept. If you revise this thing, that is a good. Still you have a confusion, then please watch one video on the YouTube and see how DC machines is work. Correct. So you can see the major components. That is a pole shoe, armature winding, yoke, commutator, brushes, and armature, and field winding. Correct. So in the case of DC machine, we can say stator winding is connect the field winding. So stator winding, it is a field winding. And rotor, armature winding. Correct. So this is the just scale out of the DC machines. So you can see the major components. So this is the pictorial view of the commutator of DC machines. So this is the pole shoe, otherwise we can see the pole, and this is the carbon brushes to collect the current. Carbon brushes to collect current. And commutator, there is your mechanical, we can say mechanical converter. Correct. So mechanical converter is, what is the use of mechanical converter? So it is changing the current the direction. Okay. So it is able to rotate the machines. Major components. So yoke, pole shoe, armature pole, field winding, armature winding, commutator, brush, shaft, and bearing. So these are the major 10 components of the DC machines. In the case of AC machines, so there is a commutator is missing. Because in the AC machine, by default, the direction is changing every time. Because in the case of the AC machine, so you can see the waveform of the AC machine is that this thing, 0 to T, and this is the, maybe we can say the voltage. So 0 to half time, there is a cycle is positive, and after that negative. So that's why it is not required the commutator. Maybe somebody asking this question in the case of the AC machine, why commutator is not required, and why commutator is required in the DC machine. Because in the case of the AC machine, by default, we can change the current of the supply voltage. Because nature is by default, there is a positive half cycle and negative half cycle. But in the case of the DC, we can say this is a constant line, correct? So there is a no rotation. Every time is a constant amplitude, correct? Yes. So this is for you. So you can just go to this slide and see what is the use of the yoke, fame, correct? I am not going to explain here in the class because you already studied this thing in the BTech level. So just revise this thing. What is the use of the yoke? If you remember this thing, then just keep. Otherwise, please go through this slide. What is the use of pole and pole shoe? Field winding, armature core. So you can see the structure of the armature core, armature winding. So we have a two type of winding. There is a lap winding and wave winding. Okay. Commutator. What is the use of commutator? Brushes. So brush is made up of the carbon. Okay. Carbon or the small machine in the electrographic. So maybe the graphic, otherwise the carbon, correct? Shaft, what is the use of the shaft? So by using the shaft, we can connect our load to the motor, correct? Bearing, without bearing, we cannot able to rotate any other part. So there is a like we can see the friction, correct? Classification for DC machines. So we will discuss the detail about the classification in the second unit. So there is a series shunt, short shunt, and long shunt. Otherwise, the field excitation base, we can say the separately excited DC machine and self-excited DC machines. So we will see detailed analysis about this type of machine in the second unit. Yes. So key point from the today's class. So we discussed the fundamental concept, then leakage flux and magnetic fingering, introduction of the machines, operating principle of the DC motor, and Fleming left-hand rule and right-hand rule, and the construction of the DC motor. Yes. So today we discussed this topic in the today's class. In the next class, we will start with the analysis of the DC machines, analysis of the induction machines, and analysis of the synchronous machines. So if you have any question, any confusion from the today's class, then please let me know. So we can discuss if you have any confusion, any query. Yes, student. Any confusion, any query from the today's class? Okay. So then I will share my today's lecture notes to the Sanjeev to you. Then you can share the lecture notes to everyone. Okay.
Okay, sir.
Okay. Then thank you so much.
Thank you, sir.